It seems strange for us to be talking about heating in air conditioning, but we do need to talk about the electric heat strips that are found in a lot of air conditioning and heat pump systems around the country, especially down in the once you get further south, as well as in apartment units up in the Northeast. So let's get a little bit into electric heating. The growth of electric heating began in the 1950s and became very popular in areas not served by natural gas pipelines. It was an alternative to oil heating in a period where cost of electricity throughout was extremely low. Throughout the same period, the electrical demand for air conditioning during the summer months was increasing. To help boost the winter demand and even out utility usage, electric utilities and heating manufacturers began to encourage the use of electric heating. There were special rates and promotional programs like Live Better Electrically and Total Electric Home. These were all introduced in the 1960s. Today, many systems provide both heating and cooling with a single air distribution system. Therefore, most air handlers are configured to accept both cooling coils and heating elements. This has reduced the number of installations for straight standalone electric furnaces, and instead electric heat is often used in combinations with cooling or heat pump systems. So typical residential electric furnace consists of a cabinet, a blower compartment, a filter, and a resistive heating section. Most manufacturers, when they're manufacturing air handlers for electric heating, provide a cooling coil as well. Some advantages are they are more compact than equivalent gas or oil furnaces. Due to cooler surface temperatures, they have zero clearance requirements on the sides. It may therefore be located in small spaces such as closets or even in wall cavities in apartment units. There's no combustion process, therefore they require no vent system or makeup air. They may be mounted in any direction. Okay, horizontal, vertical, downflow, upflow, doesn't really matter with electric heat. With electric heat, there are no losses such as those experienced with oil and gas combustion process. Therefore, electric heat is considered to be as close to 100% efficient as we can get. Remember, with gas and oil, we lose part of our heat out of the combustion process. It goes out the vent. Even with 90% efficient furnaces, we lose heat. When we don't have to vent the air, we get 100% of the heat generated into the space. Now, this slide set doesn't go into it, but there is one pretty large disadvantage with electric heat that didn't exist when it first began to become popular. Electric rates have skyrocketed across the country. So what used to be maybe a $50 electric bill to heat an entire house would now be possibly a $300 to $400 electric bill using electric heat by itself. The blower compartment is a housing that includes the filters and the blower fan for circulating the air through the system. Smaller units will use centrifugal multi-speed direct drive fans, while larger units are belt driven. Most residential, they're direct drive. An electric furnace has less resistance to airflow as compared to an oil or gas furnace, and therefore fan performance is more efficient. The heating section consists of banks of resistive heating coils. They're made of nickel chrome wire and held in place by ceramic insulators. The heater normally operates on a 208 to 240 volt power supply. So if you look at this heat section in the picture here, you'll see the wires, the nickel chrome wires. This is the resistive elements that actually get hot. This is in the airstream, so all the air coming out of the blower blows through this before it goes into the ductwork. Okay, there's two safeties down here. These are our high limits. If for some reason airflow stops across this, the high limits will eventually open before there's a chance of fire. The amount of heat produced by each heating element is affected by the supply voltage and the current flow, which together determine total wattage. 1 watt of power produces equivalent of 3.412 BTUs per hour of resistive heat. Electric power is measured in kilowatts, with 1 kW being equal to 1,000 watts. The term kilowatt hour is used to express the amount of energy used in 1 hour. So 1,000 watts, okay, produces 3.412 BTUs per hour of heat. The input of an electric furnace is given in kilowatts, and the output is given in BTUs per hour. To find the heat output of BTU per hour, multiply the kW input by 3,412. To find the kW, divide the furnace BTU per hour by 3,412. The amount of heat produced by an electric furnace is a function of the supply voltage and the current flow, because watts is volts times amps. So if our supply voltage is higher and our amperage is higher, our output is going to be higher. A furnace rated at 240 volt with a current draw of 125 amps would have a kW input of 3,000 or 30,000 watts, which is 30 kW. 240 times 125 equals 30,000. Residential furnaces' output capacities normally range from 5 kW to 30 kW. A 30 kW 240 volt electric furnace has a current draw of 125 amps, which for a 200 amp electrical panel would only leave 75 amps for other electric uses. So electric heat, what we're trying to tell you is, has a very high current draw, and you have to be very careful on the power supplies that they're attached to. We must remember that all electrical work must conform to the requirements of local code and ordinances, as well as the NFPA 70, which is the National Electrical Code current edition, or whatever edition is in effect for the area of jurisdiction. The sequencer control is an important part of the operation of electric furnaces. When a call for heat occurs, the electrical sequencer contacts close and energize the circuit. As the sequencer begins to heat up, the blower and the first heater come on. To stage the elements, there's a time delay before each additional heater is energized. The timers are set up in seconds. Example, 120 seconds will need to pass before another stage of heating element will energize. In most furnaces, these are separated into 5 kW or 10 kW, depending on what your total heat is, stages. So at the call for heat, thermostat closes, you would have your first 5 kW heat strip and the blower come on. Then 120 seconds would pass. That gives chance for the current draw to start on the first one and level out. Then the next one would come on, and so on. Electric furnaces that have multiple heat strips are designed with a sequencer that allows each heat strip to come on individually or in small groups. Most use sequencers to sequence or stage the heater operation. A sequencer uses a small heating element wrapped around a bimetal strip or PTC, that's positive temperature coefficient control. When the bimetal strip warms up enough, it snaps or warps to close a set of contacts to turn on the heat strip. Some sequencers have multiple contacts that are staged on. Staging can be accomplished by using a center pin that pushes upwards on each successive set of sequencer contacts. In some cases where multiple heating elements are sequenced to turn on, multiple sequencers are used. This is an example of a multiple sequencer. Okay, we have a stage 1 that turns on our first stage in our blower motor. Once that is operational, the second sequencer will come on. And about 120 seconds later, the second stage of heat would come on. Okay, so again, we take a look at the inside of this. Okay, we have a heating element. And when it's not energized, these contactors are open. There's a little bimetal piece of metal on here that's right now cool when it's at rest. We put control voltage into my bottom two terminals. Okay, the heater comes on and the temperature begins to rise. 30 seconds first, the thermostat closes. That first stage will come on. That first stage is normally your blower motor and your first stage of electric heat. This will continue to give off heat, and then as the stage 90 seconds later or whatever it's timed for, the second stage of heat would come on, and this would just continue to go that way throughout however many stages. The heating elements used in electric furnaces are made out of nickel chrome alloy. The nickel chrome alloy is used because it has both high electrical resistance and slows down oxidation. The material is used simply because of its resistance to oxidation, unlike many other metals that are more likely to oxidize due to high temperatures. Heating elements may appear to be long coils and are bright in color when they're brand new. However, when heated and used, they'll become discolored and eventually be a dull black color. And again, when we look at this heat strip that's over here in our picture, this portion with the spring looking material, that's in the airstream. That's the portion that heats up. You'll have 4 screws. This mounts directly into the cabinet of your air handler. You'll connect L2 to both of these terminals. You'll connect L1, one here, one there. And again, how you wire it is dependent if you want both stages of heat to come on at the same time. And this device here, that's just our high limit. Every electric heat must have a high limit. That is code. The length of the element determines its kW capacity. Electric heating elements are rated by their kW capacity and come in a pre-wired rack setup. Each electric furnace is designed to hold a specific type and size of heating element rack, and they are not interchangeable. When replacing a heating element rack, be sure that you specify the model and serial number of the furnace the rack is fit into. One common application of electric furnace is to combine it with a split system heat pump. We haven't talked about heat pumps yet, but heat pumps are reversible air conditioners. Whenever the outdoor temperature drops below the thermal balance point of the structure, in other words, that's the temperature that the heat pump can still provide heat to the building, the heat pump alone may not be able to maintain a comfortable indoor temperature. This is when the electric furnace will supply additional heat necessary to maintain the thermostat set point. One advantage of using an electric furnace as supplemental heat source in the heat pump application is that this creates a draw through the coil for the heat pump. This is the most efficient application for an indoor heat pump coil. Because of the energy conservation concerns, some cities, counties, and states have ordinances or laws that prevent straight standalone electric furnaces from being installed in new construction. This is a complete turnaround of where it was back in the 60s and 70s, where electric heat was being encouraged. Now, if you have electric heat, it is always combined with heat pumps or some other source of heat. However, a lot of times you find it with geothermal. However, you have to know how to handle this when you come across it with older units in straight air conditioning. There are single-stage and two-stage thermostat systems depending on the size of the unit. A fan control switch lever can be set to operate at low, medium, or high speed whenever the heating or cooling equipment cycle is on. Larger furnaces and some heat pumps use multi-stage thermostats. For electric furnaces, the first stage would bring on at least 50% of the total capacity. The second stage of the thermostat would respond only when the full heating capacity is needed. This is energy savings. This would be like for what we consider the shoulder seasons, the spring and the falls, where you don't need all of the electric heat and you can only use part of it. For heat pumps, the first stage brings on the heat pump and the next stage brings on the electric heat strips as needed. Air handling capabilities of electric furnaces are similar to other forced air furnaces using multi-speed direct drive blowers. Multi-speed direct drive blowers have the capacity to adjust the blower speed to deliver the required air quantity depending on the static resistance of the supply and return air duct systems. The air distribution systems for an electric furnace requires the following considerations. For electric furnaces, the air temperatures coming off the furnaces are lower as compared to gas and oil equipment. Temperatures of 120 degrees and below can create drafts if improperly introduced into the conditioned space. Additional diffusers are recommended. Direct loss through unconditioned spaces is critical, so well-insulated ducts are a must to maintain comfort and reduce operating costs. The lower the temperature air that is coming out of the registers, the more your customers are going to complain of drafty environments. Electric heat, when it first comes on, before it has a chance to warm the ducts, sometimes can be considered drafty. So a lot of times we run it at either a lower blower speed, or we add additional diffusers in a room so that the drafts are less obvious. All electric circuits have one or more safety devices to protect the system from overheating and overcurrent. Electric heating elements are protected from overheating that may be caused by a fan failure or a blocked filter. The high limit switches sense air temperature and open the electrical circuit when overheating occurs. This is a requirement, and if you ever have a bad high limit control that's preventing the heating from coming on, do not jumper it out. It is an extreme fire hazard. Even if it means leaving the customer without heat, you leave the customer without heat until you can get a replacement for the high limit. As a backup, some furnaces have fusible links that melt when the heating coil temperature goes too high due to an overcurrent condition. A fusible link is a one-time device that is wired in series with the heating element. Some manufacturers use fusible links that are mounted in ceramic. Fusible links are made of an alloy that melts at a specific temperature, usually around 300 degrees. This is the maximum level of safety since a fusible link will open instantly anytime an overcurrent situation occurs. A high limit is used to sense temperature so that in a high temperature situation, the limit will open. High limits will normally reset automatically once the bimetal strip in the limit has cooled down. So here's some pictures of these two safety devices. On the left-hand side is a fusible link. It's a one-time device. Once it breaks, you have to replace it. The high limit switch is over on the right-hand side. You saw this earlier mounted in the heat strip. Okay? High limit switches will most of the time automatically reset. Inline cartridge fuses sometimes are used to protect individual heating element, groups of heating element, or the entire furnace. These are fast-acting fuses and should be used instead of dual element time delay types. We want fast-acting. Okay, if we have an overcurrent or overheating situation, we got to deal with this fast before there's a chance of fire. Circuit breakers may be used as overcurrent protection. Circuit breakers used on the 208 volt to 240 volt systems have two breakers that are interlocked, so the overcurrent in one leg causes both breakers to open, removing power from the load. Some furnaces use more than one set of breakers so that individual parts of the heating circuit can be protected separately. Always look. Make sure that you do not have power, and the only way you're going to do that is to have a meter that you have checked all the points with before you touch anything inside a furnace. It may appear to be off, but one leg may still be hot. Built-in fusing or circuit breakers are provided by some manufacturers in compliance with the National Electrical Code. This eliminates the need for external fuse boxes. All replacement wiring used in an electric furnace must have a rating of 105 degrees Celsius. This is 221 degrees Fahrenheit with an AWM type application wire rating. This wire will stand a much higher environmental temperature which can be experienced within an electric furnace cabinet. Cannot use any old wiring. You have to use appropriate wiring. So again, electric furnaces are found a lot of times in apartment units, and once you get further and further south, they're found more often in working alongside heat pumps. We haven't talked about heat pumps yet, but the electric heat strips are an important part of the heat pump cycle.